Greetings to you. We continue our discussion with the other parameters of water monitoring. It applies also to effluent monitoring. So, today I am going to discuss with you about the determination of nitrite. Nitrite in general is a pollutant. Basically, it affects the heart and other tissues, especially with the formation of chemicals which will determine the functioning of the heart. In acid solution, normally nowadays nitrites are there in all water and effluents, and whenever there is a problem of hard water in the country, whenever there is a problem of hard water in the country, there is a certain amount of softening required, and one of the softening method is by RO, that is reverse osmosis. And in reverse osmosis, the pollutants, dissolved salts, usually pass through the reverse osmosis membrane, RO membrane, by diffusion, and then the substances which are having up to 100 Daltons are held in the membrane, and the remaining water passes through the RO membrane. So, in general what happens is the permeate is good water, but the reject concentrates almost all the salts that are rejected, and the treatment or disposal of the RO reject is a fairly difficult problem, and in this context the determination of nitrite becomes important. The normal effluent should not contain more than 45 ppm of nitrogen, nitrite I mean, and that is why nitrite has become an important parameter for the determination of water in drinking as well as potability as well as for industrial effluents. So, the principle is very simple. What happens is you react the sample containing nitrite with primary aromatic amines to form diazonium salts. This is a very well known chemical reaction. Almost all organic chemists know that nitrites react with primary aromatic amines and they form the diazonium salts. These diazonium salts are intensely colored azo dyestuffs, and whenever they react with our aromatic compounds containing an amino or hydroxyl group, they give red color, yellow color and intense colored substances. These dyes are suitable for spectrophotometry, and the reaction is very specific and sensitive. That means almost all nitrites usually end up, if you react end up giving colored dyes whenever you form diazonium salts and treat them with some aromatic compound containing amino or hydroxyl group. More than 10,000 applications of these techniques have been applied in spectrophotometry, and this is what I am presenting to you is specifically for nitrite. So, the reagent solutions are all very simple. You need to prepare stock nitrite solution, that is about 100 ppm, and your working solution would be 1 ppm. So, all you have to do is prepare 100 ppm and dilute it by 100 times to prepare the working solutions. This working solution you have to prepare daily. Okay. And the reagent solution is a sulfonylic acid solution, and it is treated with potassium hydrogen sulphate in distilled water, and NEDA, that is what we call it. You have to N1-naphthyl ethylene diamine dihydrochloride is a solution, and this also you have to prepare, but store in the dark because it is photosensitive reagent. And then this is the basic reaction. The nitrite group will react with water to give you nitric acid and HNO2. That is a very simple straightforward reaction, that is in presence of oxidizing element. And this HNO2 nitrous acid aqueous will react with C6H5SO2 SO3H, that is sulfonilic acid, to give you an azode dye. The azode dye I am representing it as N plus and N, and then this is known as disonium intermediate, and this disonium intermediate is reacted with N1 naphthylethylene diamine. That will that is simply an addition product, and the azode dye is formed. This azode dye is intense red in color, and you will have to measure the absorbance of this. So, what we do is we go about doing normal reaction, transfer an amount and required amount in 10 ml volumetric flask, and you have to prepare standards from 0 to 2500 microliter, that is approximately 2500 micrograms of nitrite solution. In normally we dilute it in 10 ml volumetric flask, and then we have to add this works out to about 2.5 ml, 2500 ml of the sample, and then 1 ml of sulfonilic acid and 1 ml of NADA solution, dilute to mark, allow it to stand for 10 minutes, and you have to measure the absorbance. Normally recommended volume is about 1 ml, that is your whenever you have an effluent, you should take 1 ml of the effluent, and even for standard you can take 1 ml, that is 1 ppm. So, 1 microgram of 1 ml 1 ppm nitrite nitrogen solution in 1 centimeter cell gives you an absorbance of about 0.32 plus or minus 0.01. That means, if you assume that the instrument sensitivity is 0.004, the 10 times dilution would be 0.1 ppm, and your detection limit would be somewhere about 0.001 ppm, 0.01 ppm, that is about 10 nanograms. So, it is a fairly sensitive reaction, and you can continue working with this very comfortably with almost all waters containing nitrate as a component. So, I want to show you this curve, that is this is the calibration curve. You can see that the calibration curve is fairly linear, and R square is value is about 0.9902, that is the linearity index. So, it is fairly decent because you will be determining 20, 40, 50, 60 micrograms only, that is about 6 ppm. So, whenever you have a higher solution, you dilute it accordingly and complete the analysis. But what I wanted to tell you is nitrite is a very important component. It is also used in the industry for nitriding. Many of these stainless steel and other metals are used toughened by molten nitrite solution, molten nitrite salt. They are exposed and heated to about 900 degree centigrade, and the waste nitrite bath will have this nitrite coming into the effluent, and also nitrite is a typical industrial effluent also. So, that completes our discussion on nitrite, and then now we move on to determination of manganese. And regarding manganese, I have to tell you that most of you are familiar with manganese in the environment. Potassium permanganate, most of you are familiar, it is dark violet in color, it is an oxidizing agent, and the oxidizing agent it is used in the treatment of water treatment. Even when the wells around your house are polluted and smell is coming, or some organic things are coming in sewage, etc., treatment with potassium permanganate is one of the standard method of well water treatment. And also in the laboratory, potassium permanganate is used as an oxidizing agent, and it is very well known. And manganese is also normally found in groundwaters at concentrations of about 0.1 ppm. Manganese is a very interesting element because it is widely distributed in the earth's crust also. So, most of the soils have manganese, and there is a requirement of the manganese measurement in the soil and water, etc., because it is a micronutrient also. So, because it is distributed widely in the soils, you can come across soils which are having elevated levels of manganese. Now, what this manganese do in the environment? The problem is elevated levels of manganese cause stains in plumbing, laundry, cooking utensils, etc. So, it is a very tricky element, and manganese is basically a very important industrial element. It is also used in the alloys, and the maximum level of manganese allowed in drinking water is 0.3 ppm. So, it is an essential micronutrient also for plants as well as animals, but higher doses are toxic. Actually, this statement is a little ambiguous. Whenever we say any element is a micronutrient, it does not mean that only micronutrient quantities we are exposed. Any material, whenever it is in excess, can become toxic. So, manganese is no exception to this rule, and it is toxic at higher levels, and it is associated with Alzheimer's disease. So, along with aluminum, manganese also people look at the manganese concentration in blood, brain, and body fluids, etc. Therefore, it is also industrially a very important chemical metal, and several methods are there for the determination of manganese. Most of them usually require solvent extraction. So, we have tried to do the analysis by sticking to aqueous solutions. That is one of the aims of this program, this teaching program, where we want to avoid extraction, at the same time permit you to determine the substances in ppm level or within the specified limits by the pollution control board. So, spectrophotometric method for manganese determination, we are proposing this 4,2-pyridylazonaphthol and Triton reagent. Usually there are so many methods for the determination of manganese. Why we have chosen this reagent is because 4,2-pyridylazonaphthol, that is known as PAN in short, 4,2-pyridylazonaphthol, PAN. It is a very commonly available organic reagent. You can buy it across the shelf. It is very easily available. And Triton X100 is another reagent that has been selected because it is a surfactant. It is a non-ionic surfactant, and the one of the jobs of Triton X100 is to keep the concentration of the micelles in such a way that it does not precipitate. So, actually several surfactants are regularly and routinely used in spectrophotometry nowadays. Earlier I have explained this type of reaction whenever we did it with the precipitation stabilization. Sometimes we have used polyvinyl alcohol, sometimes we have used gelatin, and now I am proposing that we use Triton X100 for the present investigation. Why? Because it affords a very high sensitivity of the reaction. It also gives you selectivity, and manganese can be directly determined in aqueous solution without separation from interfering elements. That is one of the advantages of the determination of manganese. So, if we look at it, This is the structure of the organic reagent. It is a ternary triphenyl 3 rings, 3 aromatic rings fused together with azo group, that is NNN, and then there is one OH group. Both these nitrogen and OH groups are electron releasing groups, and it has 4,2 pyridyl azonaphthol. This is 2,2. If I have some 3,4, if I have a OH group here, then it is known as 4,2 pyridyl azonaphthol, and this reagent can be used for the determination of manganese. So, this pyridyl azonaphthol, it forms a purple red complex with manganese. The reaction occurs in alkaline pH. That is one advantage. Very few metals can be normally determined in alkaline media. That is because most of the metals in the periodic table or whatever we come across in normal day to day life, they all precipitate as hydroxides and oxides and hydroxides in alkaline range. But in presence of Triton X100, most of these precipitates precipitation does not occur, and manganese is no exception. So, manganese at pH 9.2 is still in the form of as an anion, as a manganate ion, and if we form a complex with 4,2 pyridyl azonaphthol and Triton X100, we form the red complex, and the intensity of the color is measured at 562 nanometers. 562 nanometer is usually the typical measurement for potassium permanganate. So, this is also similar in composition, and the concentration is directly proportional to the absorbance and vice versa. And masking agent normally we use are not EDTA or CDTA, but the complexing agents which should be stable in alkaline medium. So, we have not much choice except triethanolamine, that is TEA, that is known as TEA, and potassium cyanide is also a good complexing agent, and sodium ascorbate. Instead of ascorbic acid, we use sodium ascorbate for the overcoming of the interferences. Usually linear calibration graphs are obtained with about 25 microgram of manganese. So, with this information, let us take a look at the reagents. Reagent things are very simple, that is we have to dissolve manganous sulphate as a monohydrate, and then we will have to dilute it to about 100 ml. The working standard should be 5 ppm, that is about 0.5 ml we can take and dilute it to 100 ml with deionized water. Triton X100 is available across the shelf. We have to prepare about 16% pure Triton X100 solution. We have to dilute it with deionized water. Usually Triton X100 is a very thick viscous liquid. So, normally what we do is we try to prepare on a weight basis. You can either take 16 ml or you can weigh exactly in a beaker and dilute it to 100 ml. And triethanolamine is also fairly, it is not so viscous as Triton X100, but we can prepare 16 ml of that triethanolamine in deionized water and use it as a complexing agent. We need to prepare a buffer because the pH 9.2 is a very standard buffer of ammonium chloride and ammonia. So, this is very easily prepared by dissolving 5.35 gram of ammonium chloride and 7 ml of concentrated ammonia, that is in about 100 ml of water. And the potassium cyanide, Usually people do not like to use potassium cyanide as a chemical reagent in the laboratory because it is very dangerous to use, but sometimes it becomes necessary to use such chemicals as and when required. That is the speciality and hazard of the laboratory also. So, there is not much choice if we have to deal with complexing agents. Potassium cyanide is one of the excellent complexing agent with us. Then we can go for methanolic solution, pan solution, pyridinylazonafthol. What we do is we dissolve 0.1 gram of pyridinylazonafthol in methanol and make it up to 100 ml using methanol only. Sodium ascorbate you can prepare in acidic aqueous medium, that is no problem. And the procedure involves transfer of up to 5 ppm in volumetric flask. You have to add sodium ascorbate to reduce the manganese, manganic to manganous, and 0.5 ml of triethanolamine and Triton X anhydride and potassium cyanide, and finally you have to add 4,2-pyridylazonaphthol solution to each, and you have to dilute to 10 ml with deionized water. So, we can measure the absorbance of each solution in the spectrophotometer again around 562 nanometer. As I already explained to you, it is the violet color that we are measuring, and we have to prepare a calibration curve. The calibration curve is linear up to about 25 micrograms, and 25 microgram in 10 ml will give you approximately 2 absorbance of about 0.2. So, that is very high. Normally we do not determine any material up to 2, but in this case especially why I put this up to 2 is because the concentrations vary quite a large, quite a large range, especially in the determination of molybdenum, manganese, and even if the concentration is up to 25 ppm, which is normally found in the soils as well as in some of the extreme effluent waters, you can straight away go for the determination without any dilution. That is the requirement, and R square value is about 0.998. So, that is also very good basically, and this is the spectrum of manganese pan complex. You can see that around 562 we have a peak here, and we can use other peaks, but they are not so specific, it is so easily identified, and there are shoulders etc. But this 562 is fairly readable, fairly attainable in a spectrophotometer also. And the cookbook value, recommended sample volume is up to 5 ml, and cookbook value gives you an absorbance of about 0.36 plus or minus 0.2, that is 0.038 to 0.034 using for manganese in about 5 ml of the substance. Regarding the interference, I would like to tell you that the interference from about 1000 ppm, I would like to report to you: iodide, chloride, fluoride, sulphate etc., nitrate, most of the anions, phosphate, bromide, citrate, tartrate, Triton X 100, of course we are using it as a reagent, and then SLS, sodium lauryl sulphate, all these things in 1000 ppm do not interfere, and many metal ions, cupric, cobaltous, nickelus, manganese, magnesium, calcium, antimony, silver, aluminum, silver and molybdenum, they do not interfere at 1000 ppm level. Now, we have also looked at the interference from other elements, that is vanadium, chromium, aluminum, mercury. and arsenate. These ions, cations and anions as well, do not interfere up to 50 ppm, that is 10 times value. And then equal volumes would be ferric and lead. They do interfere to some extent, but not much, because even though ferric iron precipitates as a hydroxide, it is complexed before precipitation, it is complexed with this triethanolamine. And then lead also is meets the same fate whenever we use triethanolamine. And then at 5 ppm equivalent levels, we should not worry if chromium, cadmium and zinc are there. And then EDTA also does not interfere if it is there up to 5 ppm. Now, why I want to tell you EDTA in this case is because the EDTA has become a part of our river waters, industrial waters, lake waters as well as municipal waters, because of the extensive use of EDTA in most of the laundry materials. So, with this introduction, I would like to show you the calibration, and then next we will discuss about cadmium in the drinking water.